Okay, so let us continue with the 29th exercise. This is where we ended the previous video. So we are given two functions alpha and beta, alpha from r into s and beta from s into t, so that we can form the composition beta alpha, and it's given that this composition is onto. From this we have to figure out whether the functions alpha and or beta are also onto. So let's see. We will start the solution off by proving that beta is onto, but then we will see that alpha is not necessarily onto. So to prove ontoness of beta, we have to choose any element here in this set T and show that that element has an inverse image under the function beta. So let T belonging to T be any element. Now note that the function beta alpha is onto, it is given to be onto, but beta alpha has domain R and the range, or what you sometimes also call codomain, the second set is T. So we write like this: since beta alpha from R into T is onto, there exists an element R in R such that T is the beta alpha image of R. Okay, so this thing is happening because beta alpha is onto. But then this equation can also be written as beta of alpha of R, where alpha of R belongs to the set S, because alpha maps R into S and smaller belongs to R, so alpha of R is in S. Now this equation says that T has the inverse image alpha of R under the function beta. So that means every element in capital T has an inverse image in S under the function beta. So that tells us that beta is onto. Hence, beta is onto. It's not necessarily true that alpha is onto. To see this, we of course need an example. To see this, we consider the sets and the functions defined via these definitions. So now our set R has two elements, 1 and 2, and S has three elements. So we define alpha like this. Alpha of 1 is defined to be 1, alpha of 2 is defined to be 2. Then for beta, this is the domain and this is the codomain or range. I can't remember exactly what convention is being followed in this book. When I say range or codomain in this sense, I just mean the second set, okay, the set other than the domain. So we define beta like this. Beta of 1 is also defined to be 1 just like alpha, and beta of 2 is defined to be equal to 2. But beta of 3, because 3 now is also there in the domain of beta, beta of 3 is also defined to be equal to 2. Then let us calculate the composition beta alpha. So beta alpha maps R into T. In this case, both of them are the same set. Beta alpha of 1. Alpha of 1 is 1 and beta of that 1 is again 1. Just like that, beta alpha of 2 is 2. So from this we can clearly see that beta alpha is onto. That's how we have the functions here. Note that beta alpha and beta are onto, but alpha is not onto. Beta alpha is onto, we can see from here. Beta is also onto because what is the codomain for beta? The set T, that means this. You choose any element from T, which will either be 1 or 2. 1 has an inverse image under beta, and that inverse image is 1. And 2 also has an inverse image under beta. In fact, 2 has two different inverse images under beta, 2 and 3. Only one presence of at least one inverse image is enough to say that it's onto. Now to see this entire thing at once, you can draw such a figure like this. So this is our set R. The set T also has the same things. R and T are the same. S has three different things, 1, 2 and 3. So alpha maps 1 onto 1 and 2 onto 2. So this is our alpha. And then beta maps 1 onto 1, 2 onto 2, but 3 also onto 2. So this is 1, 2, 3. So from this map, without being too specific, you just see at once and you notice that beta is onto. No element in T is left out. No element is sitting there alone, unattacked. Whereas that is the case with the element 3 for the function alpha. 3 is not the output of any element of R under the function alpha. So alpha is not 1 to 1, but alpha is not onto, but beta is onto, and beta alpha is of course onto. So this example shows that alpha is not necessarily onto. So that is the solution. And then the next exercise is similar, only this time in place of onto we have 1 to 1. Everything else is similar. These are the same. Again we have functions alpha and beta, and suppose now that beta alpha is 1 to 1. Must alpha be 1 to 1? Must beta. This time around alpha will be 1 to 1, but beta will not necessarily be 1 to 1. So let us see. We first prove 1 to 1-ness of alpha, or injectivity of alpha. Okay, for that what should we do? There are two things, two ways of showing that alpha is 1 to 1. You choose two elements from R and you assume that they are distinct, and then show that their alpha images are also distinct. That is one way. And another way is to again choose two elements from R and assume that their alpha images are not distinct, that is, they are the same, and show then that the elements are not distinct, that is, the inputs are the same. And that's what we are going to do. So let R1 and R2 belong to R such that their alpha images are the same. Now look at these two elements. They are elements where? Elements in S, and they are the same element. Now S is the domain of beta and beta is well defined. So the beta images of these two things, which are actually the same thing, should also be same. They cannot be different, because otherwise beta won't even be a function. So we directly write then beta of alpha of R1 is equal to beta of alpha of R2, or this is nothing but the composition beta alpha evaluated at R1, and this is beta alpha evaluated at R2. Now we invoke the condition, the hypothesis that beta alpha is 1 to 1. Since beta alpha is 1 to 1, this last equation implies R1 equal to R2. Because if R1 and R2 are not equal, then their images being equal under beta alpha would mean that beta alpha is many to 1, it's not 1 to 1. So contradicting the hypothesis that beta alpha is 1 to 1, so R1 must be equal to R2. But that's what we needed to show from here. Thus alpha is 1 to 1. However, beta is not necessarily 1 to 1. It's not necessarily true that beta is, or we can write here itself, beta is 1 to 1. And luckily the same example shows that fact. We have already seen the example. Now just see what we have here. This beta alpha, we have already seen that this is onto, but at the same time this is one to one also. Distinct images, distinct inputs have distinct outputs. So beta alpha is one to one, so that matches with our hypothesis. And now look at this figure. This figure directly tells you that alpha is one to one, but beta is not one to one, because of this two elements having the same image under beta. Beta is not one to one. So here we have the second solution also. Okay, next exercise 31. Let S be a set with m elements and T be a set with n elements for some positive integers m and n. Now there are two parts. How many functions are there from S to T? And in part 2, how many of these functions are one to one? Okay, the number of functions from one finite set into another is a known fact, and we have in fact already proved this in one of our analysis videos. You go to the playlist Analysis by Terence Tao. There you see that in the section on finite sets, we have in fact proved that this number is n to the power m. It's not very difficult to prove this, and the proof is by induction on m, keeping n, that's how we proved it. The author does not prove this. Tao does not prove this. Tao simply asks this in one of the exercises. So a simple proof can be obtained by inducting on m, keeping n fixed. So because in this exercise we have not been asked to provide details, so what I will do, I will just simply mention this number and I leave the proof of this fact to you. So I would write the solution to the first part like this. the number of functions from S to T is the number of elements in T, that is n, to the power, that is the number of elements in S. And to prove this, apply induction on M keeping n fixed. So either you find this proof in one of our analysis videos. I lost track of where that which video has this proof, but among the analysis videos you see those videos that in whose description you have the things about finite sets. Okay, there you will find the proof. Either you do that or you try to prove it yourself. It's not very difficult. Okay, now we come to part 2. How many of these functions are one-to-one? To see that, to figure that out, we take one small example. Say we have S with 3 elements, which we can of course conveniently take 1, 2 and 3. You can take anything you want, but this is more convenient. And say T has 4 elements. So now our M is 3 and N is 4. We want to find how many functions there are from S into T that are one-to-one. Now one-to-oneness gives us what? One-to-oneness, whatever the function is, say you have some one-to-one function alpha. What it will do, it will map distinct elements onto distinct elements. For example, you can consider this map, which maps 1 onto 1, 2 onto 2 and 3 onto 3. This is a one-to-one function from S to T. So the number of elements you have in S is the same as the number of outputs. In other words, the image of S under alpha has the same number of elements as S has. Okay, S and alpha of S have the same number of elements. So to find the one-to-one functions, you have to concentrate on those subsets of T that have 3 elements. How many such subsets are there? That number itself will not be the number of one-to-one functions, because apart from this, you can change the outputs, you can permute them. For example, instead of having this, you could have had this also. That is, say, another function alpha prime, say. This is also one-to-one. Okay, and here the images are the same, 1, 2 and 3. So from this we quickly see that the number of one-to-one functions from S to T will be this 4p3, the number of permutations of 4 objects when we are choosing 3 at a time, and distinct objects, of course, there is no question of repetition. So this number is, we know how to calculate for P3. In general, that means that since this has m elements and this has n elements, so the number will be npm, n factorial divided by n minus m factorial. Is that it? Actually, this is not the entire story, because we have not been given any restriction on m and n, or how they are related, which one is greater, which one is smaller. Nothing like that has been said. We have just simply been given that m and n are some positive integers. Note that in this particular example, our n is greater than m. N can be equal to m also. In that case also, the same technique can be applied. If n is equal to m, then you will not have any other choice. I mean, here you can include 4 also, and you can say exclude 2, and that way also you will have some permutations or one-to-one functions. I should not say permutations, but one-to-one functions. But if your n is also 3, then these are the only images with which you have to work. You can at most permute them, that's all. There is no introducing something new that is sitting there outside and removes something that is already there, you have chosen inside your image set. But if m is less than or equal to n, then this method works, and this is the number of one-to-one functions. However, m can be greater than n also. For example, you may have this situation. Say this is your S and this is your T. Then you cannot define a one-to-one function from S to T. Why? Because for the sake of one-to-oneness, say you start by defining the images of these elements under your function, and in that way you are defining the function. So for the sake of one-to-oneness, say you have chosen the image of 1 to be 1 and the image of 2 to be 2. You cannot choose the image of 2 to be 1 because you want the images to be distinct. For distinct inputs, the outputs should be distinct. But then you have run out of output. Now, because you want to define a function, this should be an input and it must have some image, and that image now can either be 1 or 2. In any case, you don't get a one-to-one function. So if your m is greater than n, then the number of one-to-one functions is 0. So let us now write these observations. We will just simply directly write the things. The number of one-to-one functions from S to T is, let's write the easier one first, 0 if m is greater than n and is npm, which is n factorial divided by n minus n factorial if n is greater than or equal to m. So that is the solution, and this part you please try to do this. If you don't get the proof, then let me know. I will show you the actual proof. And then let S and T be sets and alpha from S to T be a function. Okay, so two sets are given and a function between them is given. Nothing else is said about alpha, whether it is 1 to 1 and or onto. We don't know those things. Show that there exists a set R and functions beta from S to R and gamma from R to T such that beta is onto gamma is 1 to 1 and alpha is equal to beta composition gamma. At first the exercise may look somewhat complicated, but if you think of it for a moment, then it is actually very easy. Okay, so let us first see what we are trying to do here. This is given to us. These sets S and T are given to us, and a function alpha is given to us. Now, alpha may or may not be onto. Okay, onto. So that means the image of S under alpha, which in any case is a subset of T, that may or may not be a proper subset of T. If this is a proper subset of T, then alpha is not onto. Otherwise, if it is equal to T, then alpha is onto. And we are right now we are not thinking about one-to-one-ness of alpha. So what we plan to do here is to make this alpha of S itself the intermediate set R. And now we need a function beta from S to R and a function gamma from R to T such that beta is onto and gamma is 1 to 1. why don't we choose beta to be nothing but alpha itself? So originally the the possibility of alpha not being onto is now gone. Why? Because if there was something in T outside of alpha of S, we have removed that possibility, because we have removed whatever is there in T outside of alpha S from T, and we have obtained alpha S itself. So as a function from S to alpha of S, alpha is onto, and that alpha is now beta. So this beta is onto, and this is our alpha of S. But then we need a function gamma. For that, what we do, we just take the identity function. I should not say identity function, because alpha of S and T may not be equal. Alpha of S may be a proper subset of T. This function actually is called inclusion function. If you have a subset A of B, then the inclusion function, I am writing ID here, which denotes identity, but it's actually inclusion. The inclusion function from A to B is the function which maps every element of A onto itself. Now, because A is contained in B, these outputs are again in B. So this is a well-defined function, and this is called inclusion function, and sometimes it's denoted by this symbol, an arrow like this. Okay, so that is our plan. So let us now see how we can write the solution accordingly. So let R be alpha of S. Define beta from S to R by beta of S equal to alpha of S, and gamma from R to T by gamma of R equal to R. Okay. Note that beta and gamma are well defined. Let us see one by one. You take any small s from capital S. You calculate the beta image of that. By definition, that is nothing but the alpha image of S. And since the alpha image of S belongs to the alpha image of the entire set S, which is nothing but R, so our output is in R. And since this beta has been defined in terms of an already well-defined function alpha, so everything is okay with beta. So beta is well-defined. And then what about gamma? To calculate gamma at R, where R is any element here, what you do nothing. The output is also R, and that R belongs to T because alpha of S is a subset of T, and originally R has been chosen from alpha of S. So this is also well defined. Also, beta is onto and alpha is 1 to 1. beta is onto because we have how have we formed beta? To form beta, we have not actually done anything to the formula for alpha. The formula is intact. The formula for beta is nothing but that of alpha. We have just changed the codomain. Originally it was t, we have replaced that by alpha of s. So now beta is onto, and like that gamma is 1 to 1 because here distinct inputs give us distinct outputs. That is because outputs are nothing but inputs. Okay. Furthermore, for any we are starting from S now, so for any S belonging to S, we see that beta gamma S will be equal to what? Wait, am I doing it correctly? Beta gamma, is it beta gamma or gamma? Yes, yeah, that's why it's not matching. Gamma beta, sorry about this. Gamma beta is because beta gamma does not make sense. Gamma beta is the composition of beta and gamma, which will map S into T. For you take any element of S, on that first you apply beta, you go to R, and then on that element you apply gamma, you go, that takes you to T. So beta gamma S, or gamma beta S is gamma of beta of S. Now beta of S is what? Alpha of S, and alpha of S by definition belongs to R. So that means alpha of S can be chosen in place of this small r, and according to the definition of gamma, this is nothing but alpha of S. It does not, gamma does not change the input. The input itself is the output. So that means the functions alpha and gamma beta have the same effect on every element of capital S. Hence, the functions are equal. So that completes the solution. Okay, next we go to the exercises, the next set of exercises. The first few are of course quite easy and things we have already done, but just for the sake of completeness we are again going to do it. Show that for any positive integer n Okay, so this can be proved by induction. should I do this? This is so easy. This one you do yourself. We have already done this. I think in quite a few times we have done this in this channel itself. The next one also we have done, but this one I will do for you. Show that for any positive integer n, this identity is true. 1 times 2 plus 2 times 3 and so on, plus n times n plus 1 is equal to n times n plus 1 times n plus 2 divided by 3. The given identity is true for n equal to 1, because if n is 1, then the left hand side is just this first term, 1 times 2, so that is 2. And what is the right hand side? 1 plus 2 will be 3. You can cancel 3 with this 3 in the denominator. In the numerator we have 1 times 2. So they are the same. Assume that the identity is true for some positive integer n. Okay, so now we need to prove it for n plus 1. One times 2 plus 2 times 3. When you when you use dot like this to represent multiplication, keep in mind that this dot is in the center, somewhere in the middle between the bottom and the top. If you write the dot here, that means 1.2. Okay, that does not mean the multiplication operation. So to denote multiplication operation, you write the dot somewhere in the middle. N times n plus 1 plus n plus 1 times n plus 2. So because of our induction hypothesis, we know what this part is, or rather we know a compact expression for this part, and that expression is nothing but this. So this is equal to n times n plus 1 times n plus 2 divided by 3 plus this extra term n plus 1 times n plus 2. So we can now do what? We can take this thing outside. So in the first term we will have n will be left out, and in the second one, adjusting everything, you will have 3, so that when you multiply this with 3 you get this numerator. So now you see that you have n plus 1 times n plus 1 plus 1 times n plus 1 plus 2 divided by 3. So that has the same form as this, but n plus 1 in place of n. This completes the induction and proves the identity. The next exercise 2.3. I should not say 0.3, 2.3. That is the third exercise in the second chapter. Show that for any positive integer n, the following identities hold. And these are the identities. This time, because of the presence of binomial coefficients, we are going to use the binomial theorem to prove them, not induction. Induction is a power-free technique, but sometimes not using induction is smart. N choose 2, n choose 3, etc. plus this is equal to 2 to the power n, and the alternating sum gives us 0. Here we can solve both parts 1 and 2. I will just simply give the hint. The rest is, you can figure it out easily. We know from the binomial theorem course, we know that for any real numbers a comma b and any positive integer n, your usual binomial expansion is this. plus, let's write one more term, on that side n choose n minus 1 a b to the power n minus 1 plus n choose n b to the power n. Okay, this is something we already know. To prove the identity in part 1, take a equal to b equal to 1. If you do that, on the right hand side you will get a finite sum, and that finite sum is this, and on the left hand side you have 1 plus 1 whole to the power n, which is nothing but 2 to the nth power. Like that, to prove the identity in part 2, take a equal to 1 and b equal to minus 1. Okay, so that will give you the alternating sum on the right side and 0 of course on the left side. So you please complete this. And then after this, I won't solve it today in the next video, but this is a very interesting exercise, the next one. It's about plain Euclidean geometry. Let us just see the exercise at least. In the plane R2, let us draw n lines. But not just any lines in this particular way. No two of which are parallel. And at the same time, no three of which meet at a point, that is, no three of which are concurrent. Into how many regions do they divide the plane? Let us see some values of n and what happens when you consider those values of n. N lines means you can take n equal to 1, you can start from there. So if you have only one line, which can be any line actually, because there are no other lines here in this situation. So these extra conditions are trivially true for just a single line, and the single line divides the plane into two distinct regions, okay, on either of its two sides, on either side. In place of this, if you have two lines, now the first restriction will come into play, no two of which are parallel. So because these two lines are not parallel, no matter how you draw them, there will be some point of intersection somewhere, okay, and these two lines divide the plane into four distinct regions. Now if you have three lines, then not only are they not parallel, no two of which are parallel, but say two of them are like this. If you want, you can draw them perpendicular, that is allowed, but parallel is not allowed. But then now you have another line, and that cannot pass through this same point, because no three lines should pass through the same point. So it will be something like this, for example. Now how many regions do we get? 1, 2, 3, 4, 5, 6, 7. Here we have 2 regions, here we have 4 regions, here we have 7 regions. And here we had one line. From one line we have got 2 regions, from 2 lines we have got 4, and from 3 lines we have got 7. We will see in the next video that from n lines we will get I believe it is 1, this many regions. Let's try these values here. If you put n equal to 1, then of course 1 plus 1 is 2, and that 2 and this 2, they cancel each other, and you are left with 1, and that 1 plus 1 is 2. So this is okay. If you put n equal to 2, then here you have 3, and this 2 and that 2, they cancel each other, so 3 plus 1 is 4. And when you have 3, then here you have 3 plus 1, which is 4. If you divide 4 by 2, you have 2. Multiply that with 3, you get 2 times 3 is 6, 6 plus 1 is 7. So we will see how one can prove this. Okay, there are different ways of proving this, but I have found one. I have not found it personally, I mean I've found on the web. We will see that proof. It looks very interesting. So we will do these things next Saturday. So that will be all for tonight in release algebra exercises. And you can comment on the comment section below if you want to say something about these things. And tomorrow there will be our analysis video. And day after tomorrow, on Monday, we will have Galilean. Okay, so with this I end this video. So see you tomorrow. Until then, have fun with mathematics. This is me, Lucifer, from A Mathematical Room. Have a nice night.